Hello, and welcome back to Stat 2050 at the University of Wyoming. Online, having a great time, I'll tell you what. Okay, so it's a new week. That means we're doing new stuff, which is great, I think. And we're going to start with a concept, and it's only a concept. There's not a whole lot of math that goes into it, at least for you. There's a whole bunch of math that goes into the proof of it, but we're not going to worry about that, because that's really something. But since it's a new week, let's talk about the album of the week, I'll tell you. Nathaniel Rateliff and his album, And It's Still Alright. Holy. It's too good. It's too good, especially the title track, And It's Still Alright. I mean, it'll make you cry, you know. Especially if you're not the crying type. Especially if you're not the crying type, you'll cry. And also all the other songs are good too, but that song especially is great. He's the same person from Nathaniel Rateliff and the Night Sweats. They're a great band too if you're into more like kind of bluesy, kind of like folky rock kind of stuff. But this whole album is super good, and a lot of the songs are really fun. So highly recommend you check it out. All right, so let's get into stats. Okay, so we have this idea of the central limit theorem, and it sounds kind of complicated, but I promise it's actually a pretty simple concept, and it's pretty elegant too. Oftentimes in statistics, we work on samples to sort of approximate the population. Sometimes we know what the population looks like, but other times we don't. And that's okay. That's okay. Which is fine, right? It is okay, because the central limit theorem says, whatever, I don't care. So let me, instead of giving you a bunch of math and stuff, let me draw a picture. Let me draw a scenario here. So let's say that we have two people. One person is happy. Look how happy. And one person is indifferent. No, hold on. Okay, that's pretty indifferent. Okay. And let's say they're both doing an experiment. Let's say that they're doing an experiment on some population, right? And let's say within this population, they don't know what it looks like, but we do. And let's say that there are like 8 units within this population. Okay, easy enough, right? We know this, but they don't, which is fine. And let's say that this population, as we know, has some mean, right? Pretty much every population will have some mean, regardless of how it is distributed, okay? Now let me tell you why this person is happy. This person is happy because they have a lot of money to do science. And so they are able to grab, let's say they grab 6 people or 6 things, whatever it may be, for their study. And then what they're going to do is they're going to record X bar, and we'll call it X bar 1. And that'll make sense here in just a second. The reason why this person is indifferent is because they don't have a lot of money. Who knows what their situation is? They're probably like a grad student or something. Or maybe an undergrad, doesn't really matter, the situation, just building a world here. Let's say they only have enough money to grab 3 of the 8. Okay, and what they're going to do is they're going to record X bar, and that's going to be X bar 1 for them, right? Okay, now, who do you think is going to be closer to mu? Is it going to be the happy person, or is it going to be this indifferent person? Well, we can already kind of tell that X bar 1 here for the happy person is encompassing more of the population than this X bar is, right? X bar 1, the purple one here, only has 3, whereas X bar 1, the blue one, has 6, right? And there's some overlap in those samples by themselves, right? They don't know that they're both working on the same population. It's okay. It's fine. So we see here that this X bar 1, the blue one, is most likely going to be closer to mu than this one will be. Okay, they still might be close. But this one certainly is going to be telling maybe a better story than this one. Okay, that's fine. So they go on and do their experiments, and then that's that. Okay. Well, let's say that they go out and do the same experiment again in the same process, right? They want to solidify their results. Okay, so what they do is they still have the same amount of money. Instead, though, let's say that this person samples these 6. Okay? And what they're going to do is they're going to record X bar. This time it's X bar 2. Same deal here. I can't remember what color I used. They only grab 3 again, and let's say that they grab these 3. Okay? Come down here, and then they record X bar 2 for them, right? Who's going to be closer this time? Well, same logic as last time. X bar 2 here, for the blue, for the happy person, will be closer to mu, closer to the population, than X bar 2 for the indifferent person will be, okay? So that's all fine. That is all okay. So more consistently, with this sample size here of 6 each time, more consistently will be closer to mu than the smaller sample size will be. However, they eventually will both approach the population mean. It'll just take longer for this one, right? It'll take longer for the indifferent person to get there because randomly, let's say that they grab 3 each time, whenever they grab this 3, and then this 3, and then record all those X bars. Eventually you'll get every combination that eventually will lead to the mean of the population. Now, let me draw that out because this is the whole idea with the central limit theorem. This idea of sample sizes and the population mean and the sample means. So let's say that they go ahead and plot on a histogram all of their sample means that they get, all of their X bars that they get. Okay. It turns out that, because we work on a random kind of basis here, right? It turns out that the distribution of those sample means, the distribution of the sample means of the X bars here, will be normally distributed for both of them. Interesting. However, it turns out that since the sample size here was large enough, the normal distribution for this one will look something like this, where its mean here turns out to be mu. Same value, okay, with a very little spread on each side, right? Okay. Now for the indifferent person down here who's only grabbing a sample size of 3 each time, their distribution of those sample means will be a little bit fatter. Maybe it looks like this, right? We don't discriminate, but this is what it looks like. Okay, and it turns out that that sample mean is also mu. But what do we see? Well, we see that there's more spread here. There's more spread. So eventually, it kind of approaches the population mean. It eventually approaches mu. But it takes longer to get there, and you have more sort of variation around the mean than you would here. Okay? And that's the central limit theorem. What we're saying here is that the sample sizes were large enough that we got close to mu, right? Whereas here, the sample size was fairly small, and it would take more samples to get closer here, right? And that's why we put so much emphasis on having a adequate and large sample size if everything is random, right? If everything is random. Whereas here, we kind of see that the story is, a little bit different. Still gets to the end, just takes longer. Okay, so here is the mathematical definition of the central limit theorem because, I think the picture does better, and I'll show you another thing here at the very end. But the mathematical definition is that if n is sufficiently large, the sample means of a random sample from a population with mean mu, standard deviation, sigma, blah, 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 are approximately normally distributed with a mean. Okay, and there's a little bit of inconsistency here with what I say and what the world of nerds say. Mu x bar is just x bar. And standard error, so that's something a little different than we're used to seeing, but same concept. It's more or less standard deviation. Sort of, we can use that in the same way. Sigma, right? We traditionally use S if we're working with the sample, but that's okay. You'll see a bunch of different things all over the place. But the big thing there is this idea of standard error instead of standard deviation. It's telling you the same thing. It's just a different kind of context sort of situation, right? So let me draw it out again. So we have I'll draw the distribution of the sample means, right, of the X bars. Looks something like this. always normal, right? Always normal. Why is this so much bigger? Whatever. With some mean mu x bar or x bar, whatever, and then some standard error, right? Standard deviation. Same deal. We're just talking about sample means instead. So no biggie, no big deal. The English definition is fairly simple. The distribution of all sample means or proportions, right? So this is just saying some kind of percentage, right? Is normal. The distribution of sample means is normal, as long as the sample sizes are large enough. That's what we kind of saw in the picture that I drew earlier. And the big thing here, this is the best part. If the population distribution is not normal, if it's something else, if it's some wacky thing, I'll draw some fun ones for you, right? It could be a normal distribution, whatever. It could be an exponential distribution. It could be this kind of exponential distribution. It could be, gosh, so many things. It could be like a chi-square distribution, where it looks like this, whatever. It's all gross, whatever. It doesn't matter what the population looks like. It does not matter at all. The sample means will always be normally distributed. And that's the whole idea with statistics, right? We work in samples so we can relate it all back to the population. And if we know that the distribution of sample means is always normally distributed, then we can do everything in statistics. It's beautiful. Now, there are a few exceptions to the rules as far as this goes. The original population, I can only think of one distribution that this does not apply to. It's called the Cauchy distribution. It's gross. It looks like this. But it actually doesn't have a mean. It's weird. It doesn't have a standard deviation. It is all undefined, but that doesn't show up in nature, so we just say F it and move on, okay? So, generally, though, the idea is that the sample size should be 30. I hate that, but that's kind of a rule of thumb. We've talked about how it can be much less, but the general idea is 30. Now, I will never ask you that, and most people don't even require that. It's just sort of an artifact of the past. But 30, whatever, it's fine. Okay, so now let's go online to see this actual process again. And I recommend that you do this side by side, because we'll get slightly different things as far as the process, but the outcome will still be the same. I think it's pretty dope. Okay, so let me clear all of this. This is what it looks like, okay? And so with your finger, let me put my pen here too. Whoop. Sweet. With your finger, with your mouse, depending on what you're watching this video on, you can draw a population any way you want, right? So that's a kind of a normal-ish distribution, right? We can go like this, make a kind of a more narrow normal distribution, whatever. We can even do some uniform. We can do some skewed, whatever. I'm going to do a custom one just to show you this point, okay? So I'm going to draw a normal distribution, and it looks gross. It looks gross. But let's take a note here sort of at the margin. The mean of this distribution that I just wrote is 15.05. We'll just say that it's 15. Easy enough. The median is 15, blah, blah, blah. The standard deviation is 5.5. Okay, no big deal. So that's what the population looks like. Let's talk about getting some samples. Let's get some samples, okay? So what this is going to do, and let me turn this one off for just a second. Okay, what this is going to do is I'm going to tell it to grab 5 things from this distribution. Okay, let me show you. 1, 2, 3, 4, 5. Totally random, right? Totally random. This is all random. So if you were to do this side by side, you're going to get different stuff, different values, and that's fine. Let's do it again. So what this is doing is grabbing 5 things, and it's showing you on the second plot here where those 5 things are coming from, and then it's going to take the mean, and then it's going to plot the mean, plot the value for the mean. Okay, so right now we only have one x bar 1, we'll say. And this is maybe just one experiment, totally fine. Let's do it again. 1, 2, 3, 4, 5, take the mean, plot it. Okay, so right now we got some new stuff that showed up. We have a mean of 0. That's fine because we only have 2 things. Standard deviation of also 0. That's fine because we don't have anything else. But let's do it one more time just to see. 5. Okay, sweet. All right. So with a sample size of 5, with a sample size of 5, we take the mean, plot it. Do it again. One last time. Plot it. Okay. Now, instead of doing this a bunch of times, I'm going to do it 5 times. The same process, all right? Maybe 10 times. What do we start to see? The distribution of these sample means is starting to look kind of normal. And I only had to do this 14 times. Let's do it again. Interesting. Again and again and again. So now I'm at 30 times. So 30 times of grabbing 5 things, taking the mean, and plotting it. And already we can kind of see that the distribution of this stuff looks fairly normal. What else do we see? Well, the mean of this distribution is 12.69, and we're getting close. We're getting close. We're only grabbing 5 at a time, but we're only about, 2.5 units away from the mean, from the population mean. Let's do it 5 more times. The mean is getting closer and closer and closer and closer. Okay, I'm going to skip around a little bit. I'm going to do it 10,000 times. Okay, let's see what that looks like. Whoa. So at 10,000 repetitions of grabbing 5 things, taking the sample mean, we see that the distribution of the sample means, the mean of that, this middle point here, I know you can't see my finger, but the middle point here, 15.05, well, hold on. Whoop, there it is. The mean of the parent population is also 15.05. Interesting, right? Interesting. So we're saying that if your sample size, in this case, we're only grabbing 5 things at a time. We're getting pretty close to the population mean, right? And in statistics, we know that we work more frequently with summary statistics, the mean specifically, than we do with each individual number, which is fine, right? So we're able almost to kind of equate these two things. Let's do it again. Let's do it 100,000 times, 200,000 times, 300,000 times, so on and so forth. Check it out. The mean of the distribution of means is 15.04 this time, barely a difference between the population mean. And look at that normal distribution. It's pretty wild, okay? Let's clear this. Let me draw a new population. Doesn't matter what it looks like. I'm going to draw it like this. I'm going to draw something out there. And I'm going to draw that, okay? Gross, right? Super gross. This is what our population looks like now. And now what I'm going to do is what I drew earlier, right? Where we have 2 people sampling from the same population. The first one, this third plot down here, will be a sample size of 5. So the indifferent person. But the last plot down here is going to be the happy person who's taking, let's see, what's the max? 25. They're going to be grabbing 25 at a time, okay? Who's going to get closer to the population mean? Well, we already kind of know. So let me show the animated version here. I'm only going to do it once because it takes a while. So we grab 5 for the first one, plotted it. And then we're going to grab 25. Look at all this. Totally random. Plotting it, okay? So already pretty close. Let's skip ahead 5. Let's skip ahead 10, 15, and 20. Uh-oh. Who is closer? Who has a more normal distribution, right? It's going to be the person grabbing 25 at a time rather than 5. And we can already kind of see where this is going. The means are close, right? 16.48 and 15.89 is close to our mean. Our new mean of our population is 16.82. So who is closer? It's going to be the person grabbing 25 at a time rather than 5. So we'll skip ahead 10,000. Check it out, right? What's happening here is they're both pretty close, right? However, we get more variance with the person only grabbing 5 at a time. We are not getting that close to the population mean. Whereas with the distribution of the means, when you grab 25 at a time, is more consistently close to the population mean, right? Here it is 16.83, 16.82 at the very top, 16.84 for the n equals 5 for the sample size of 5. And then that's only a little bit off, only a little bit, but check out the standard deviation, right? We get less variance with this n equals 25 than we do with the n equals 5. So let's skip ahead a ton. So we just did this experiment 500,000 times, all right? And what do we see? We are getting more close, we are getting more consistently close to the population mean with this n equals 25 than we are with n equals 5. The means are both the same, which is wild, but we are getting closer to the actual mean when we have a larger sample size, and that is it, right? The take home here is that the bigger the sample size, the better, right? And even with n equals 5, we do get close, but we're going to be missing it here and there, right? Whereas with n equals 25, we are going to be incorporating more of the population, right? We're going to be incorporating more. Okay, now, let me go back here, because this is crazy, all right? This is like a law of gravity. Explain gravity to me. Well, you can go in and say force equals mass, whatever, blah, 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 blah. I took physics years and years and years ago. I don't care. What I can tell you, though, is that if I drop something, it's going to fall to the ground, right? Same thing in the central limit theorem. It just happens. The bigger the sample size, the better we are, right? The bigger the sample size, the closer we get to the population. And the more times we do an experiment with a bigger sample size, the more, the faster we'll get to the population, right? Regardless of what the population looks like, which is dope. Okay, so the take home again. This. Whoop. Bigger sample size, the better. And that's that, right? That is that. So I encourage you to use this tool side by side or go like dork around with it all you want because it's pretty cool. And we'll call it there. So I will see you in a little bit.